Hello students, this is the recording for the Units 4 through 5 exam for Physics SCI102A. Let's go ahead and start off talking about question number 1. So question number 1, you're either taking a look at mechanical waves or electromagnetic waves. Everyone has a different question, so make sure that you read yours carefully. So taking a look here, regardless of if you are a mechanical or an electromagnetic wave, remember that all waves, their purpose is to transfer energy. So again, this is actually for both types, mechanical or electromagnetic waves. Now, on the other hand, they do have some very key differences here. So taking a look, mechanical waves do require a medium or a physical substance, matter, such as water, air, or other gases, or solid materials like the earth, steel, etc., etc. A good way to think about this is remember that mechanical, think about how like a mechanic physically works with a machine. So when you're thinking mechanical, you should be thinking of the word physical, okay? The energy does get passed particle to particle. That should make sense because it requires a medium which has particles, right? So medium has particles. Okay, so that energy gets passed from one particle to another particle. Some examples here are things like springs, things like sound, which gets passed through air. Medium is air, particles. Or things like, for example, ocean waves. All of those things require a medium. Okay, so those would be examples of mechanical waves. Here we go. Perfect. All right. And now let's go ahead and talk about electromagnetic waves. So electromagnetic waves, again, also transfer energy, right? We know that. However, they do not require a medium. So this means that since they don't actually require any physical substance, they can actually travel through the vacuum or empty space of outer space, right? So they can travel through areas like outer space, which has no matter, is empty, what we call a vacuum. So there's no gases, no solids, no liquids in outer space. It's just empty, which is pretty cool. It's important that we actually can, it's important that we can actually travel through outer space, that these can travel through outer space because these give us light as well as heat, right? So the sun, for example, has electromagnetic waves, so it gives us both the light that we see as well as the heat that we feel. And if it couldn't travel through outer space, then we would all die because there would be no heat or light to reach the Earth. All right, so pause the video. This should help you with question number 1. Again, read carefully. Everyone does have a different question. Continue playing when you're ready. Okay, so question number 2 is talking about the 3 different types of mechanical waves. Remember, mechanical waves meaning physical, right? So mechanical waves means that they are physical, which means that all of these different types are going to need a medium. All right, so if we're taking a look at longitudinal, or if we're taking a look at transverse or surface waves, all 3 of these are going to need a medium. Okay, now let's go ahead and talk a little bit about their differences though. So longitudinal waves, again, still require a medium. However, in this case, the particles move parallel to the direction of energy. So what this means is that if my energy, for example, is traveling from my speaker to my ear, in the case of sound is a great example of a longitudinal wave, the particles are going to be pushed parallel, which means that they are also going to move back and forth along the same direction. Again, remember that their particles just wiggle back and forth. They never actually leave their space. Only the actual energy is traveling. So we can see here that the energy overall is traveling. So here's our energy on top, and the individual particles just kind of wiggle back and forth in their spot. Much like how in a stadium wave, everybody kind of stays in their seat. Okay, so these particles are moving back and forth parallel to that energy. Another example here would be a spring, right? If I push on a spring, same thing here. You can see that the individual springs, let me grab a different color here. The individual springs here are moving back and forth in their spot. And again, that overall energy is moving in the parallel direction. All right, let's go ahead and now take a look at transverse waves. So let me erase all this stuff. Again, transverse waves are still mechanical. So again, they are still physical. They still require a medium. But this time, when we talk about transverse waves, their particles actually move perpendicular, which means they're going to move kind of in the 90-degree angle. Okay, so if we take a look here, for example, we can see energy traveling to the right here. But what the actual individual particles are doing is they're actually moving up and down. Okay, so the particles move perpendicular in a transverse wave, and you can see that happening here, where this particle on the string, if this is a guitar string, for example, is going up and down. Same thing here, you can see this particle going up and down, this part of our matter going up and down. All right, so that actually is perpendicular, right? If I were to extend that line, it would actually cross over my energy. Okay, so that tells me that this is a perpendicular wave. So again, particles are moving up and down. We can see this in a rope, right? So each part here is moving up and down, even though our energy overall is going to the right. So this is perpendicular, and we can see that there. All right, question number 2 continued, taking a look at surface waves. Again, surface waves, just like everything we've talked about so far, are still a mechanical wave, all right? And so they will still require a medium of some sort. They are a physical type of wave. So surface waves, the particles actually move in a circular motion, and they happen at surfaces. So where the two surfaces of a medium's touch, that is where a surface wave will happen. Seems pretty obvious. So for example, where air meets water in an ocean wave, or where air meets the earth in an earthquake wave. Those are where two different mediums are touching, air and water or air and earth, and so they will create a circular motion. So you can see here that again, the energy might overall be traveling to the right, but the individual particles are just moving in circles. All right, again, nobody's leaving their seat, everybody kind of stays in their seat, but you can definitely see that these particles are moving in a circular motion here. Please note that particles near the surface actually do make bigger circles, which means that they have more energy, right? So if you think about a really big wave coming towards you, it's actually a lot better to duck underneath the water because these ones have less energy. They're not making as big of circles. All right, so at this point you should be able to answer question number 2, regardless of if you're taking a look at longitudinal, transverse, or surface waves. Pause the video, continue playing when you're ready. All right, question number 3 is asking about the different parts of a wave. So remember that we learned this different vocabulary. We learned that the crest and trough are both points. All right, so this is important to remember that these are actual points. So the crest is going to be the point at which we have the maximum upward displacement from equilibrium to the top, right? So this is going to be from the equilibrium, which is the middle part, to the highest point. All right, so you can see the crest right here. These are all crests, all right? So equilibrium to highest point, okay? And then trough, on the other hand, is going to be the part where we have the maximum downward displacement. In this case, we're going to the lowest point, right? So we can say, I guess I don't need to retype that. There we go. So this one will be the lowest point. All right. So you can see a bunch of different troughs right here. Okay. But again, either way, these are points. So make sure when you're taking a look at these on your problem that you're making sure that the points are labeled as crest or trough, depending on if it's the highest point or the lowest point. All right, let's go ahead and take a look at amplitude and wavelength. Amplitude and wavelength are actual distances. So amplitude is the distance in terms of the height of either a hill, so from equilibrium to a crest, the point of a crest, or the depth of a valley, so from equilibrium, the rest down to the lowest point, the trough. Okay, remember that we'll talk about this a little bit later, but that the more amplitude something has, the more energy it has. All right, so you can see some examples here of amplitude. I'll go ahead and highlight these in green here. So here's an amplitude, and here's an amplitude. Again, it's either from rest to equilibrium to the top, or from equilibrium to the bottom. Okay, wavelength on the other hand is just the length of a single wave cycle. You can either measure this from crest to crest or trough to trough, or from any identical point to any identical point. So you can see here moving down across the equilibrium to where we're moving down across the equilibrium. That would also be the wavelength, and we can see that it starts to repeat after that wavelength. So a single wave is a single repeat here. Okay, and again, you could do it from any identical points to another identical point. But again, wavelength is going to be a distance or a length of one wave. Obvious, very obvious name of that vocab word. Okay. I do want to be clear that for question number 3, again, that A and B here are distances. So A is a distance and B is a distance or a length, right? So these are actual distances, whereas C and D are points. And again, that's really important to understand because we talked about 2 different points and we talked about 2 different distances. Pause the video, continue playing when you're ready. All right, question number 4. This is an example of how to find frequency. Everybody has a different version, so please don't copy this one. Nobody has this version. All right, but this is just an example. All right, so just an example. Please do not copy. Okay, so remember that the frequency is the overall number of cycles in 1 second. So you can see here that I have an overall second of my wave here, and I'm going to need to count the number of overall cycles. Okay, now remember that a cycle, all right, is going to include here, if we were to go from 2 identical points, it's going to include a top bump and a bottom bump. Okay, so let's go ahead and take a look at where we see that happening. Okay, so one wave cycle has a top bump and a bottom bump. All right, so let's go ahead and take a look down here. Okay, so if I were to start here, right, so we start at 0, and I follow this along, you can see a top bump and a bottom bump, and then it's going to start repeating again, so top and bottom. All right, so after my first top and bottom bump, all right, this right here is just one wave. All right, so here's one wave overall. Okay, let's go ahead and do this again. So again, we can now see a top bump and a bottom bump, and then it'll start to repeat. All right, so here's my second wave. Again, top and bottom, here we go. Here's my third wave. Top and bottom, here's my fourth wave. Here's my fifth wave. Sixth wave. Seventh wave. And eighth wave, all the way to 1 second. All right, so again, we can see here that from here to here, that's my fourth, fifth, sixth, seventh, and eighth waves. Don't count the actual dots here. Again, we're counting the number of overall waves, right? So I can see one big wave here, 2, 3, 4, 5, 6, 7, 8. All right, so we have 8 cycles in 1 second, which again, the units for that is then hertz. Right, so in this case it would be 8 hertz. Again, this is just an example, don't copy it. Your units though for question number 4 should in fact be hertz, HZ. Make sure you only spell it as HZ, otherwise the computer will mark it as wrong. Okay, again, do question number 4 on your own with your own problem and pause the video, continue playing when you're ready. Okay, question number 5 is how to find period. So period, on the other hand, is the time for just one wave to be completed. So taking a look here, remember that this is actually a period of time, and so our units here should be S for seconds. So make sure for question number 5 that those are the units that you put in. Otherwise, again, the computer will mark it as wrong. You should be putting in S. All right, so what we need to do is just find a single wave. Again, a single wave is going to be a top bump and a bottom bump, because after that it starts to repeat, top, bottom, top, bottom. All right, so taking a look here, I have a top bump and a bottom bump right here, so this right here would be my single wave. All right, let me go ahead and clear that. Here we go. So this right here would be my single wave from here to here. Single wave. All right, and then all we need to do is take a look at the time. All right, so taking a look at the time right here, you can see in this example, the time for this would actually be let's see if I can change the colors here. The time for this would actually be 0.2 seconds. All right, so the time here, time would be 0.2 seconds. And so my final answer right here would be 0.2. Again, do not copy this because this is not no one has this example. Everyone has a different one. All right, but again, in this case, you would see that the time for a single wave, taking a look at our timestamp down here, is just 0.2 units would be seconds. Again, do question number 5 on your own for your own example and then for your own problem, and then continue playing when you're ready. All right, so question number 6 says it takes blank seconds for a single wave cycle to occur. Calculate the wave's frequency. Everybody has a different time. All right, so you will need to make sure that you are filling in your own time. All right, so we have this equation where F equals 1 divided by period. So F is frequency, 1 divided by capital T, which is the period. And remember that frequency gets measured in hertz, whereas period gets measured in seconds because period is a time. All right, time for a single wave. All right, so the time it takes for a single wave to occur, calculate the wave's frequency. Again, taking a look here, if this is seconds right here, this should be my, let's see here, let's go ahead and label this. This right here should be my period. All right, so we're going to take this number in seconds and plug that in for my period. Again, in your calculator, you should put the 1 first, then divide it by your period, the time here in seconds, and that will give you your frequency. You should round to 1 decimal place. All right, so let's remind us of that. It should have 1 digit after the decimal, so point whatever, point blank. And then your units here, again, we are solving for frequency, so units here should be HC for hertz. Pause the video, continue playing when you're ready. Question number 7 is then asking for the reverse to calculate period based on frequency. So this requires the other equation here. So remember that T again is still period in seconds and F is still frequency in hertz. All right, but this time we're kind of switching them. So period, we want to calculate the period of a blank hertz wave. Again, everyone will have a different number here, so make sure that you read this carefully. So plugging this in, this would be hertz, so that gets plugged in for frequency. Again, in your calculator, the number 1 goes first, then divide by the frequency. Taking a look here, that will give you your numerical answer, and then your units here, again, should just be for period. So your units here should actually be S for seconds. Only the letter S, sorry, let me actually type it here. Only the letter S, otherwise the computer will mark it as wrong. Pause the video and continue playing when you're ready. All right, question number 8 is asking you to calculate speed. This first equation, speed of a wave, has speed, which is meters per second. It has up here the upside down y, which is called the lambda. Again, that's wavelength measured in meters, and then capital T is period. We already learned that one, measured in seconds. All right, so taking a look here, I have a sound wave travels blank meters in blank seconds. What is its speed? Again, don't forget that everybody will have different numbers here and we'll have a different question, okay? So taking a look here, blank meters, remember meters is our unit for wavelength, all right? So I should know that this right here is going to actually be my wavelength. So this number right here should get plugged into the first spot here. And then in blank seconds, remember blank seconds, seconds is my unit for period or time. And so that should get plugged into my second part of my equation right here. So taking a look at that, what I end up with is you should be dividing the wavelength in meters by the period in seconds. Again, don't forget that this first number here comes first, then divided by the period in seconds. That should give you your number here. And then don't forget that your units here, because we're solving for speed, should be m/s for meters per second. For this question, you do need to round to 1 digit after the decimal to the tens place, so you should have point blank. Pause the video, continue playing when you're ready. All right, question number 9. Sorry, I did forget to mention that for question number 7, you should have 3 decimal places. So 1, 2, 3, point blank, blank, blank. All right. Question number 9 here. A blank hertz sound wave has a wavelength of blank meters. What is its speed? Remember that we learned a second equation that can also solve for speed of a wave, but this time it, instead of period, it actually includes frequency, and frequency is the opposite of period. So now instead of dividing by period, we're actually multiplying by frequency, the opposite, right? So wavelength still in meters, and then frequency here in hertz. All right, so taking a look here, a blank hertz, again, hertz right here tells me that this is going to be my frequency. And over here, my wavelength in meters, right? So that's obviously my wavelength. It literally says that. So this wavelength should get plugged into the first spot here. And this frequency should actually get plugged into the second spot here. And then we just multiply them together. So your wavelength times your frequency, multiply those two numbers together to get your answer here. And again, don't forget to have one digit, so point blank. And then your units here, again, we are solving for speed, so units here should still be meters/seconds. Pause the video, continue playing when you're ready. All right, question number 10 is asking about frequency, amplitude, frequency related to pitch, and amplitude related to loudness. So remember that frequency and pitch are directly related to each other. So frequency is how many cycles there are in a second, or your hertz. Pitch, on the other hand, is how you observe that frequency, right? So pitch is an observation, frequency is a measurement, but they are related to each other. Things that are high frequency also sound high pitched. So this would generally be more like a woman's voice, whereas over here, sorry, I should say woman's voice. Here we go. Whereas generally, low frequency is going to be low pitch. This is generally like a man's voice, obviously, kind of just overall, right, in general, what you might think. Okay, so if you see lots of waves close together, again, that's going to be high frequency, that's going to be high pitched. If you see waves spread apart, that's a lot less waves, so low frequency, more low pitched. Okay. Now, on the other hand, if we talk about amplitude, amplitude is the height of the wave. We already learned that, but this is actually related to how loud the actual sound is. So previously we talked about the type of pitch, but you could have a quiet woman's voice and a quiet man's voice, or you could have a loud woman's voice or a loud man's voice. So the pitch here is not actually related to its loudness. Instead, amplitude is where we get loudness, because amplitude is related to energy. Remember, we talked about earlier, larger ocean waves have more energy, more amplitude, and so they hurt more as they hit you. So this is also true with sound. The larger your amplitude, the more energy something has, and so it sounds louder. Whereas the smaller the amplitude or the height of the wave, the sound wave, the less energy it has, and so it sounds quieter. Again, you can still have the same frequency even if your amplitude changes, right? So again, you could have, you could be playing the violin, which is high pitched, but depending on its amplitude, it could be quiet or loud. Same thing with a woman's voice, which is high pitched. It could still be quiet or loud depending on the amplitude. Same thing with a male's voice, which is low pitched, could still be quiet or loud depending on the amplitude. Okay, so this kind of just shows us how all of these things can be mixed together, right? So the shorter you are, the quieter you are, right? So this would be a quiet instrument. This would be a loud instrument, because we can see the shorter you are, quieter, the bigger, louder. On the other hand, if you take a look at the actual number of waves, you can see that this is really spread out. And so this would be more like a cello, which has a really low pitch and a low frequency. So low pitch, low frequency. Okay, and over here, this one is much higher pitched because it has a higher frequency. We can see more waves in that amount of space there. So much higher frequency, therefore higher pitched. Okay, so when you talk about question number 10, again, if you're looking for something that's loud, you want something that has a big amplitude, which means that it's tall. Okay. If you're looking for something that's quiet, it should have a small amplitude, which means that it's short. Okay. If you're looking for something that is low pitched, like a male's voice, you want a low frequency, which means less waves, versus high pitched. All right, like a female's voice, you would want something that has a high frequency, which means more waves. Okay, so you need to find the mix there for question number 10. Everyone has a different question, so you need to find the mix that makes the most sense for question number 10, right? So find the one that, if you want loud, is big, if you want quiet, is small, and then based on their frequency. Low pitch, low frequency, the one with less waves, or high pitched, high frequency, the one with more waves. All right, so you need to find the mix that best suits those. Pause the video, continue playing when you're ready. Okay, question number 11 is asking you to find the speed at which something would need to travel faster than in order to create a sonic boom. Remember, a sonic boom is when you travel faster than the speed of sound. So sonic boom, travel faster than the speed of sound in that medium, right, which is just the physical substance, and therefore sound builds up and gets released all at once, creating a boom. All right, so it creates a really loud noise. Happens with airplanes, for example. Okay, now you are going to have different versions. Everybody has a different version, so this is just an example. Again, please do not copy my example because nobody has my example. Okay, so do not copy this example. Nobody has this example. Okay, so the question here is, an object in helium gas would need to move faster than what speed to create a sonic boom? Well, taking a look here, in helium gas, the speed of sound is 1007 meters per second. So to make a sonic boom, I would need to travel faster than that. I would need to travel faster than 1007 meters per second. All right, so taking that over here for question number 11, again, this is my example. Do not copy my example. All right, so for my example in helium gas, right, I would need to move faster than 1007 meters per second. Okay, so do not copy my example. This is just an example. Okay, now let's go ahead and figure out how do we actually convert that from meters per second, right, which is our original units, into Mach, because remember, it's much easier to talk about planes if we talk about their speed in Mach, all right, which is very fast speeds. Okay, so taking a look here, I'm going to go ahead and start off with the number that I know, which in this case is the number that we just determined. So this 1007 here, for example, would get plugged into here. Okay, so the units I'm going to include here, you must include units, is I'm starting off with meters per second. Okay, now I want to get rid of meters per second, so in the next step I need to put it on the opposite side, which means it needs to go on the bottom. And I want to turn it into Mach, that's what I'm solving for, so those units should go on top. Make sure that you do include your units. If you don't include units, you do lose points, okay, because you can't do stoichiometry without knowing what your units are. Okay, now again, we start off with the number that we know. Again, everyone's number will be different. Everyone's number will be different depending on the gas your problem is asking for. Okay, so don't copy my example. Again, do not copy my example. All right, I'm going to go ahead and just make that a different color. Okay, all right, so whatever your number is, though, that's what goes into your node. Now for your conversion, remember that we talked about how there are two different conversion options. You can either do 1 Mach over 343 meters per second, or you could flip it and do 343 meters per second for every 1 Mach. Now taking a look here, I need the one that has Mach on top and meters per second on the bottom, right? So I'm going to go ahead and take a look here. So I need the one with 1 Mach on top, so I'll fill that in. And on the bottom, 343 meters per second, all right? Now from here, this is just a regular multiplication problem. So on top, I'm going to again start off with the number that I started with. Again, yours will be different. So mine in this case would be 1007, but yours will be different. Times whatever else is on top, in this case is the number 1. You don't need to include units in this part. On the bottom, we've got 1 times 343. Okay, so now all you need to do is solve for what you get on top. All right, so here's the number that should go on top, and then solve for what you get on the bottom, And then don't forget that this is just a fraction, and fractions are just division in disguise. So then just do the top number divided by the bottom number. Remember that in your calculator, the top number comes first. So in calculator, top number goes first, okay? Again, make sure that you calculate those separately, otherwise the calculator might spit out something wrong. So calculate the top number first, then the bottom one on, then do the top divided by the bottom. And that should give you your final numerical answer right here. And then you do need to round to the hundredths place, so you do need 2 decimal places, so point blank blank. And your units here matter. You do need to also include units here. So at this point, taking a look at analyzing our units, we got rid of meters per second, meters per second. I should end up with Mach here. All right, so right down here, my final units should in fact be Mach, M-A-C-H. All right, so pause the video. Again, do your problem will look different. Pause the video, continue playing when you're ready. All right, so questions 12 through 20, feel free to continue working on those. You have seen all of these things before, so you should be able to do questions 12 through 20 on your own. However, if you do want more support, please be aware that the video for the remaining problems will be uploaded tomorrow on Thursday. Again, that is also the same day that the exam will actually be zeroed out. So it's like a 2-day exam. It'll be zeroed out at the end of school on Thursday, so make sure that in the morning you're working on questions 12 through 20. Unless you want to do them today, again, feel free to continue working on them today if you feel confident in them. Thank you so much, everyone, and we'll see you later.